You know, for pretty much all of human history, our relationship with the cosmos was, well, simple. We looked up and we wondered. But at some point, a huge shift happened. We stopped just looking and we started measuring. And that one change, that single pivot, transformed the entire universe from a divine spectacle into a physics laboratory. Today, we're diving into the incredible story of our cosmic toolbox.
I mean, think about it. How did we get from simply sketching out constellations to actually taking a photograph of a black hole's shadow? It's a journey that covers centuries of genius and innovation, from hand-ground glass lenses to telescope networks the size of our entire planet. But this story isn't just about better gadgets. It's about a fundamental shift in how we ask questions about the universe.
And here's the crucial thing to understand. It's all a chain reaction. Every new instrument we build, every new discovery we make, it doesn't just give us answers. It unlocks a whole new level of even deeper, more complex questions. It's this amazing compounding cycle of discovery that has taken us from wondering where we are to asking what we are.
So, let's start at the beginning, with the first great revolution. This was all about our sense of place. It wasn't just about seeing more stars, it was about seeing our own position in the universe in a completely new and honestly humbling way.
It really all kicked off with Galileo. In 1610, he points his little telescope at Jupiter and sees moons orbiting Jupiter, not Earth. And just like that, the idea that everything revolves around us was shattered. Fast forward to 1835, we managed to measure the distance to a star for the first time, and suddenly the terrifying, unimaginable scale of the universe just snapped into focus. But the final knockout punch to our cosmic ego, that came in 1923, when Edwin Hubble proved that all those fuzzy little smudges in the sky were entire other galaxies, making our Milky Way just one tiny island in an ocean of billions.
And you can see this shift perfectly in the kinds of questions we started asking. We went from this very self-centered, does everything revolve around us, to the much, much grander question, are we the only galaxy? Each new tool didn't just give us more data, it completely reframed our reality.
Okay, so just as we were starting to get our heads around this huge universe filled with galaxies, we made another shocking discovery. What we could see was only a tiny, tiny fraction of what was actually out there. A second, even stranger revolution was about to begin.
This quote really nails it. We found out that the universe was communicating in all these other languages that our eyes just couldn't see. Radio waves, X-rays, infrared. It was like we'd been peering at the cosmos through a tiny keyhole our whole lives, and suddenly someone threw the door wide open.
Think of it like this. Visible light, everything humanity had ever seen with its own eyes, is just one tiny sliver of the entire electromagnetic pie. If you want to see the whole picture, like the cold, dark clouds where stars are born, or the super hot gas swirling into a black hole, you need new senses. We had to build radio telescopes to hear the hearts of galaxies and X-ray satellites to see stars explode.
And what's so wild is how often we just stumbled onto this invisible universe by accident. The first time we detected the center of our own galaxy, it was just annoying static on a transatlantic radio line. The actual echo of the Big Bang, that was a persistent background hiss that scientists tried to get rid of for months, thinking their equipment was faulty. It just goes to show you sometimes the biggest discoveries aren't what you're looking for, they're in the noise you're trying to ignore.
So, we've gone from seeing visible light to detecting the invisible. But now we've entered a third, absolutely mind-bending era, multi-messenger astronomy. We're not just looking at the universe anymore, we are starting to listen to it.
And what we're listening for are gravitational waves. Now get this, these aren't light, they're not particles, they are literal ripples in the fabric of space-time itself, sent out by the most violent events imaginable, like two black holes smashing into each other. For all of history, light was our only messenger. Now we have a new one.
And in 2015, we heard them, for the very first time. A full century after Albert Einstein predicted they existed on a blackboard, we finally built a machine sensitive enough to hear the universe shake. It was an absolutely monumental achievement.
The technology that pulled this off it's hard to even comprehend. These observatories, called LIGO, use lasers to measure the distance down these super long tunnels. We're talking 2.5 miles, with insane precision. When a gravitational wave from a black hole collision passes through Earth, it stretches one tunnel and squeezes the other by a distance thousands of times smaller than the nucleus of an atom.
And from that tiny, tiny wiggle, we can actually hear the sound of that cosmic crash.
So here's why that's a total game changer. This new sense lets us witness things that are completely dark. I mean, two black holes merging, they don't give off any light at all. Before LIGO, they were basically ghosts, totally undetectable. Now we can hear them. We've opened a window onto the dark side of the universe.
Which brings us to today, and what is maybe the most profound revolution of all. We've gone from looking to seeing the invisible to listening. But now our most powerful tool isn't a lens or an antenna. It's a mathematical model.
We have completely flipped this script. The question is no longer just, hey, what's out there? Now we often start with a theory, with a prediction that comes purely from mathematics, and then we go out and build a purpose-built billion-dollar machine just to see if the universe agrees with our equations. It's a huge shift from being passive observers to being active interrogators of reality itself.
And you can see this incredible pattern everywhere. Our models told us galaxies were spinning way too fast to hold together, so we built instruments like the Rubin Observatory to hunt for the invisible dark matter that must be there. Einstein's math predicted exactly what the shadow of a black hole should look like, so we built a virtual telescope the size of Earth to go take a picture of it. The Big Bang Theory predicted a faint afterglow, so we built satellites to find it, and we did.
And the side effects of this kind of theory-driven science can be just amazing. For instance, your Wi-Fi, the wireless network you're probably using right now, it exists because a group of Australian astronomers were trying to detect faint radio signals from tiny evaporating black holes. A search that, by the way, totally failed. But in the process, they invented the complex math needed to clean up those signals, and that math is now the core of modern Wi-Fi. How cool is that?
So where does this all leave us? What are the next grand cosmic mysteries that are pushing us to design the next generation of our cosmic toolbox? Well, there are three absolute giants looming on the horizon. First, what in the world is this dark energy that's pushing the entire universe apart at an accelerating rate? Second, the big one. Are we alone? And can we find signs of life on a planet around another star? And third, a real head-scratcher. How did the universe's first monster black holes get so huge so quickly? And check out the incredible stuff we're building to answer them. We've got the Roman telescope, which will map out dark energy's influence. The aptly named Extremely Large Telescope will try to take the first actual photos of Earth-like planets. A space antenna called LISA is going to listen for the gravitational whispers of those first black holes merging. And maybe, just maybe, the future Einstein telescope will finally hear the echoes from the Big Bang itself.
And this really is the ultimate takeaway. For thousands of years, we made up stories, myths, and legends to explain the patterns we saw in the sky. Today, we start with the math. We start with the physics scribbled on a piece of paper, and then we build these incredible billion-dollar machines for one reason: to see if our human logic, our calculations, actually hold true across the entire cosmos.
It just leaves you wondering, doesn't it? Which of the wild, brilliant, totally abstract theories that physicists are working on right now, the ones that only exist as lines of code or equations on a whiteboard, which one of those is going to be the reason we build the next great observatory? And what new mysteries will we uncover when we finally turn it on?